Tonight marks a significant moment for our solar system. A third known interstellar visitor, called 3/Atlas, is about to pass unusually close to Mars at a distance of roughly 28 million kilometers. Every active orbiter around Mars is focused on studying this rare event and collecting as much data as possible. What makes this encounter especially intriguing is the object's striking green glow, subtle but unexplained changes in its velocity, and a chemical composition that doesn't match what scientists typically see in comets. Before long, it will slip beyond our reach, and once that happens, only the instruments around Mars will be able to observe it. The big question remains, is 3/Atlas simply an unusual type of comet, or could it represent something artificial that challenges our understanding of extraterrestrial technology? As the clock ticks down, there's a chance we'll detect signs like fragments separating from the main body, unexpected transmissions, or patterns of light that could redefine how we think about interstellar objects. The next few hours may reveal something extraordinary, or they may confirm that established science still holds the answers. We have just 6 hours left to observe 3/Atlas before it vanishes from Earth's line of sight as it slips behind the sun. Its rapid passage near Mars coincides with our planet's limited view, narrowing the observation window. This brief communication gap is entirely due to the current planetary alignment, not any malfunction or lack of preparation. During this time, Mars becomes the only vantage point in the solar system where detailed observations are possible. All major orbiters, including MAVEN and Mars Express, are now increasing their observation frequency, following carefully designed protocols while remaining ready to respond to any unexpected developments. Inside the MAVEN control room, the highly trained Red Watch team is now overseeing operations. These specialists are prepared for emergencies and follow detailed procedures to handle any unexpected situation. In the hours leading up to the blackout, they rehearse rapid transitions between standard data gathering and more focused, high-resolution measurements, ensuring they can immediately respond if a sudden energy spike or alert about potential debris appears. All preset configurations are activated, and coordination checks with the TGO and Mars Express teams are completed. Every command is documented, and every piece of incoming data is duplicated for backup. With Earth unable to observe, there is no room for a single failure to compromise the mission. Timing is carefully planned. Mars Express will capture a rapid series of images, which will later be combined to detect even the tiniest fragments breaking away or shifting course. TGO's sensors will scan Mars's surroundings for unusual light signatures that shouldn't exist, while MAVEN's instruments will monitor the upper atmosphere for any changes that might suggest interaction with the passing object. All spacecraft are operating at maximum capacity, with every observation window calculated to the second. Should space debris pose a threat, Mars Express can quickly switch to safe mode, prioritizing protection over continued data collection. The threshold for halting operations is set just above the last significant rise in atmospheric density readings. The period when Earth is unable to communicate is more than just a blackout. It's a crucial test of every scientific instrument deployed around Mars. The Red Watch team manages commands and data transfers during brief communication windows, focusing on maintaining the functionality of all systems and coordinating closely with surface rovers like Perseverance and Zhurong. In mission control centers, countdown clocks continue to run as the mysterious object approaches. Outside, groups of amateur astronomers are stationed with telescopes, ready to detect the first hint of any increase in brightness and relay their findings to the Global Alert Network. Over the next 6 hours, the outcome of this observation and the answer to whether Comet 3I/Atlas is simply an unusual cosmic body or something artificial, it will rest entirely on a handful of satellites and the teams operating them. The situation is tense, and there is almost no margin for error, with time quickly slipping away. Every second counts. Unusual signals have been recorded following 3I/Atlas ever since it was first spotted. The earliest sign came from an amateur observatory in Pune, India, where astronomer Priya Rallo noticed a repeating pattern in the light, a rhythmic brightening and dimming that couldn't be explained by any known comet behavior. Her observations sparked widespread attention, and the anomalies became more pronounced once professional telescopes began monitoring the object. Light data revealed that its brightness was increasing at steady, predictable intervals, far too regular to be caused by natural outgassing. The bursts of light appeared and vanished abruptly, almost as if being deliberately switched on and off. Even as the object drew closer to the sun, this consistent pulsing pattern remained unchanged, unaffected by its proximity or solar glare. A further surprise came from spectral analysis. Instead of the expected signature of water vapor, carbon dioxide dominated every reading, raising even more questions about the true nature of this enigmatic visitor. The amount of carbon dioxide present is far greater than expected, at least 8 times more than water, an unusual ratio rarely seen in typical comets. This unusual chemical composition is so difficult to reproduce that laboratory simulations struggle to match it. Surrounding the object, a vivid green glow dominates, peaking at a wavelength of 516 nanometers, and this feature has been consistently detected by instruments on both Earth and space-based platforms. Familiar explanations such as C2 swan bands or emissions from carbon monoxide fail to account for the brightness and stability of this green light. Even more unusual is the fact that the nickel emission is significantly stronger than that of iron, reversing the usual trend observed in comets within our solar system. Photographic imaging and spectral analysis add further complexity to the picture. The comet's green glow is also linked to strong negative polarization, a trait more often associated with certain asteroids than with icy cometary bodies. The dust tails contain particles that are noticeably larger and slower moving than those found in typical comets, following broad, smooth trajectories rather than chaotic ones. This pattern suggests that the material is being steadily released rather than ejected in sudden bursts. Meanwhile, precise tracking of its motion reveals tiny, irregular changes in velocity, adjustments that don't match any known models of gas-driven propulsion. Each shift in speed coincides with a flash of light, hinting at a direct relationship between the two. None of these unusual characteristics stand out alone as definitive evidence of something extraordinary, but together they describe an object that resists easy classification and does not fit into any familiar category. All the data gathered so far, from light measurements and color analysis to precise tracking of its movement, continues to build a list of peculiar features that demand explanation. The evidence is clear and plentiful, yet it still lacks a single theory that can account for every observation at once. Most researchers have approached the mystery using the familiar foundations of physics and chemistry. 4 main hypotheses, each based on established scientific principles, have been proposed to explain the object's unusual behavior. The first suggests that its unusual chemical makeup originated in an extremely cold environment. According to this view, 3 Atlas could have formed far from any star, where water remains frozen, while gases such as carbon dioxide and carbon monoxide are abundant. This would be consistent with what we know about comets from the Oort cloud. However, none of those bodies have displayed such an extreme carbon dioxide to water ratio, surpassing 8:1. Still, given the vastness of interstellar space and the small number of comets we've studied, it's possible that a single outlier could redefine our understanding of comet chemistry. A second theory focuses on the comet's internal structure. It's possible that deep pockets of trapped gases could rupture once sunlight penetrates the outer layers. If these pockets are unevenly distributed, they might produce the regular brightness changes observed. Laboratory experiments have shown that even slight temperature variations can trigger sudden bursts of gas, and under the right conditions, these eruptions can repeat if the material is layered in specific ways. Although such consistent patterns are rare, they could occur in a comet that has been altered over billions of years in space. A third explanation considers the role of dust. The comet's green glow and the presence of large, slow-moving particles could result from unusual dust composition or particle size. Interactions with the solar wind and Mars's weak magnetic field might also shape the dust tail, causing charged particles to drift into broad, curved paths rather than dispersing randomly. Models of comet tails indicate that under certain conditions, larger dust particles can drift behind the main body, moving in slow, curved paths that resemble the observed outbursts. The strong negative polarization, more typical of asteroids, could point to dense, carbon-rich particles rather than the lighter, icy material expected from a comet. Some scientists also emphasize that our current models may be incomplete. With only 2 interstellar objects previously examined, each new discovery pushes the limits of existing simulations. The small velocity shifts and precisely timed bursts we're seeing might represent physical processes not yet included in our calculations, possibly involving subtle interactions of sunlight, gas emissions, and rotational effects. In this view, the unusual behaviors are not evidence of intent, but rather a reminder of how much remains unknown. In investigating each unexplained feature, researchers are determined to eliminate every conventional explanation before considering more extraordinary possibilities. For the next 6 hours, Mars remains the only observation point in the solar system. 3 orbiters, MAVEN, Mars Express, and the ExoMars Trace Gas Orbiter serve as the primary sources of data. Each mission contributes in a unique way as the object passes by. MAVEN's specialized camera scans for faint light in the tail, watching for fragments breaking away or sudden eruptions. Its particle detectors and magnetic field sensors are set to maximum sensitivity, ready to detect any changes in Mars's upper atmosphere. A sudden rise in charged particles or a shift in the magnetic field could signal processes beyond standard cometary chemistry. If dust or energy from the object interacts with the atmosphere, MAVEN will be the first to detect it. Mars Express, equipped with both standard and specialized cameras, captures continuous image sequences to monitor the diffuse region around the object for any signs of splitting or structural change. Its spectrometer scans for unusual light signatures, unexpected emissions, or a noticeable absence of water vapor, all potential clues to the comet's true nature. Aspera 3, which studies plasma, scans for high-energy charged particles that could reveal unusual interactions between the comet and Mars' environment. The NOMAD and ACS instruments aboard the ExoMars Trace Gas Orbiter examined the comet's gas cloud, looking for abnormal concentrations of specific elements or distinctive molecular patterns not typically seen in our solar system. Meanwhile, the KSSIS camera attempts to capture images of the object breaking apart or releasing bursts of dust. Data from each instrument is time-stamped with precision and shared instantly among various research teams. On the Martian surface, the Perseverance and Zhurong rovers search for additional evidence, such as unusual dust deposits, changes in atmospheric conditions, or unexpected visual displays in the sky. Although their sensors and cameras provide valuable supporting observations, they are less sensitive than the instruments in orbit. The protocols are strict and specific. Teams monitor for fragmented structures, trajectory changes following energy releases, unusual light or radiation patterns, element ratios that deviate from solar norms, and any evidence of deliberate timing in bursts or velocity changes. Any anomaly must be confirmed by another instrument. A single detection is not considered sufficient. Only when multiple sources report the same phenomenon does it move from being merely unusual to potentially significant. Every piece of information gathered from Mars undergoes thorough verification before being analyzed. Data is duplicated to ensure safety, and each transmission from orbit is recorded, time-stamped, and stored at multiple ground stations on both sides of the Atlantic. This redundancy guards against disruptions from solar activity, transmission errors, or the rare possibility of data corruption during the communication blackout. Because delays in receiving information, sometimes lasting hours, are unavoidable, teams immediately prioritize reviewing any data that indicates fragmentation, unusual light activity, or sudden changes in trajectory. No single sensor or team is capable of responding to an alert on its own. Every potential event must be verified by at least 2 separate instruments before it is taken seriously. All original data is uploaded to public repositories as quickly as possible. Procedures for handling collected material go beyond simple cataloging. If even a minute particle of dust or ice is captured by a spacecraft's collection system, planetary protection specialists are immediately involved. These experts ensure that strict protocols are followed at every step. Samples are sealed, labeled with barcodes, and documented with digital records. Both NASA and JAXA must grant approval before any analysis begins. The goal is to maintain an unbroken record of the sample's origin. If evidence of life is ever detected on Mars after the flyby, it must be traceable back to its exact source. Future missions searching for life rely on knowing with certainty what material originated on Earth and what was native to Mars. Even details such as the time of collection, precise location, and instrument settings are stored in tamper-proof formats so that any unusual result can be reviewed and verified later. Beyond mission control, a complementary network is also active. Amateur astronomers, from backyard setups in Pune to fully automated telescopes in Arizona, contribute light and positional data to shared databases. An individual observer might be the first to detect a sudden change in brightness, but scientists immediately examine these submissions for accuracy. Official announcements are only made after multiple independent observations confirm the event, and the public is reminded to remain patient and cautious. Extraordinary claims demand strong evidence. Pre-drafted communications for different scenarios are designed to emphasize transparency and avoid exaggeration. The entire system is structured to inspire trust, with built-in safeguards, multiple layers of verification, and detailed tracking of every piece of data. All of this ensures that when a conclusion is finally presented, it is one the world can have confidence in. Inside the Redwatch control room, a central decision-making system guides every conversation and action. It operates on 3 possible assessments: normal, risky, and extraordinary, each based on the incoming data from Mars. The normal status is selected when all unusual observations can still be explained by rare but natural cometary behavior, such as sequential gas eruptions, dust with unusual chemical properties, or minor velocity shifts that remain within expected scientific limits. A risky situation is declared if fragments begin breaking off excessively, if more than 10% of the object's mass is lost, or if its path changes in a way that could endanger Mars orbiters. In such cases, the priority shifts from scientific observation to protecting spacecraft and preserving critical data. The extraordinary category is reserved for something far more unusual and requires at least 2 separate confirmed anomalies. These might include repeated signals synchronized with subtle velocity changes or light patterns that cannot be linked to any known chemical process, and they must be verified independently by multiple instruments and research teams. A single strange reading is never enough. The guiding principle is clear: only when several independent lines of evidence align can the possibility of an intelligent origin be considered. Everyone in the control room knows the stakes and the importance of each decision. In moments of significant discovery and potential scientific breakthrough, the framework now guiding planetary research serves as a crucial roadmap for what must happen next. Recent strategies emphasize a dramatic shift in how humanity responds to encounters with objects originating from beyond our solar system. It is no longer acceptable for mission teams to hold on to valuable information for months before sharing it. New protocols require that all data collected during a flyby or close approach of an interstellar object be released publicly within mere hours of its confirmation. The era of restricted or delayed access to comet observations has ended, replaced by a commitment to transparency and global collaboration. Major space agencies, including NASA, the European Space Agency, and the Japan Aerospace Exploration Agency, have pledged to support this new standard. Their approach ensures that verified data, complete, unedited, and accompanied by clear explanations, will be uploaded to publicly accessible servers almost immediately after it is received and validated. To make this rapid release model effective, advanced automated systems now play a key role in detecting and highlighting unusual or unexpected signals as soon as they appear. This allows researchers to focus their attention quickly on the most significant findings. Alongside these automated alerts, detailed calibration information is stored and shared alongside the primary data, ensuring that scientists and enthusiasts alike can analyze the results accurately. For Mars-focused missions in particular, emergency protocols now include frequent and high-speed data transmissions during short-lived or unpredictable events, followed by comprehensive releases of high-resolution imagery and full data sets. The involvement of the global public has also been elevated from passive observation to active participation, marking a fundamental change in how scientific discoveries are made and validated. This collaborative model now extends beyond professional research teams. Organized amateur astronomy networks across the world are officially integrated into the data pipeline, contributing their own observations and measurements directly to verified platforms. Specialized software then automatically sorts, checks, and ranks these contributions, flagging the most relevant information for deeper expert analysis. This means that a critical detection, and even if first noticed by an individual with a backyard telescope, can trigger an official investigation in a matter of minutes rather than days. Such inclusivity not only accelerates the research process, but also broadens the scope of who can meaningfully contribute to humanity's understanding of interstellar phenomena. Equally important are the enhanced safety and contamination protocols that now accompany planetary exploration. According to the latest directives from the Committee on Space Research, every indication of biological activity or chemical signature linked to life must be clearly marked and tracked from the moment it is detected. protected. Detailed records are required for every instance of handling extraterrestrial dust, soil, or organic matter, creating a transparent chain of custody that ensures both scientific integrity and planetary protection. These guidelines are not limited to missions currently in development. They are designed as permanent measures for all future endeavors involving material from beyond our solar system. Together, these advancements reflect a new era of openness, precision, and collective responsibility, one in which the study of the cosmos becomes a truly global endeavor, united by shared access to knowledge and a coordinated approach to exploring the unknown. On October 3rd, 2025, the celestial object known as 3/Alas made an extraordinarily close pass by Mars, approaching within just 0.19 astronomical units, a proximity that immediately drew the attention of every active mission around the planet. In response, all major orbiters and surface vehicles coordinated their efforts to monitor this rare event. Over a continuous observation window lasting more than 40 hours, spacecraft such as Maven, Mars Express, and ExoMars TGO transmitted an unprecedented volume of high-resolution data back to Earth. Their instruments captured striking details: a vivid green glow radiating from the object, a rhythmic fluctuation in its brightness, and a spectral signature that contained a surprisingly high concentration of carbon dioxide. These characteristics did not match those of any comet or interstellar visitor previously documented, suggesting that 3/Alas might possess properties unlike anything encountered before. Although current scientific models are able to account for certain aspects of these observations, such as the chemical composition and some of the orbital mechanics, there remain features that defy straightforward explanation, most notably the slight but measurable variations in its velocity and the precisely timed nature of the light pulses remain puzzling. These anomalies have led to spirited debate within the scientific community, and while the raw observational data has been released publicly for independent analysis, the most pressing questions remain unresolved. What physical process, for example, could produce such coordinated bursts of light? Could natural phenomena alone account for the data? Or might some form of advanced technology, perhaps even non-terrestrial, be involved? Regardless of the ultimate explanation, the close passage of 3/Alas has already left a lasting mark on how humanity approaches future encounters with interstellar objects. The coordinated observational campaign demonstrated the power of collaborative science across multiple missions, while the open release of all collected data has set a new benchmark for transparency and global participation in space research. Moreover, the lessons learned from this event are likely to shape how astronomers design future monitoring strategies, ensuring that we are better prepared for subsequent visitors from beyond our solar system. Whether 3/Alas turns out to be a peculiar natural body or something far more extraordinary, its brief passage near Mars has fundamentally reshaped our understanding of interstellar phenomena and deepened our curiosity about what or who might be traveling between the stars.